Looks like starting time, so let's get started. Who here can tell me the difference between, with regard to an electrical circuit, the difference between series and parallel? Okay, since all of you are trying to answer over each other all at the same time, let's try with just a show of hands. Who can tell me the difference between series and parallel? Okay, so two of you can't. All right. What is the difference between series and parallel? Okay, that's a good answer. So when things are in parallel, they all have the same voltage. When they're in series, they all have the same current, right? All right. Here's a trick question. Is that battery and that resistor in series or in parallel? They're not in parallel because the same voltage across the battery is across the resistor. But there's two, see, 1, 2. Thank you. Series and parallel describe the relationships between loads or between sources, but not both. That is an important thing to learn, and it's a good starting point for this chapter. I suspect that this chapter is going to be review for most of you, or all of you, and it may even be a little bit tedious, but it's still important. What if we put 3 resistors in series? What is the total equivalent resistance? Say again? No, we get to Kirchhoff's in a day or so. Total is 15 and 15 is 30. Why? That's right. Why? That's true. But I want you to think deeper than just rote memorization of what you've learned. I want you to think analytically. Think about what are you doing and why is the equivalent resistance the sum of the 3 resistances? Or better yet, what if we did this? Now what is the equivalent resistance? equals what? No, not quite. No, just algebraically, what does this equal to? No, it equals the reciprocal of the total resistance. The statement is that in series, the net resistance or the equivalent resistance or the total resistance, whatever you want to call it, in series is simply the sum of the resistances. In parallel, it's the reciprocal of the sum of the reciprocals. In other words, if you wanted to find out RT, you would take the reciprocal of both sides and you'd end up with so that the total resistance is the reciprocal of the sum of the reciprocals. But again, why is that true? Okay. No, the voltage, when they're in parallel, whatever voltage is across this one is across all of them because they all have the same voltage here and here, here and here. So the potential difference across any one resistor is going to be the same as the potential difference across the others. That's the definition of a parallel loads in a circuit. Hey, good morning. What I want to do today is I want to take and look at these relationships, but I want to look at them more deliberately. I want to take this one step at a time so you see mathematically, algebraically, why this works out the same. Tell me if any of you recognize this. Do any of you recognize that formula? Say again? No, just the equivalent resistance. How many of you know that formula is what this reduces to in the special case that you only have two resistors in parallel? If you're only dealing with two parallel resistors, then that's a quick way to find out what their equivalent resistance is. But if you have more than two, you have to go back to foundations, back to the general case. So, let's look at first the series case. Do y'all prefer positive or negative or electron? Positive flow or electron flow? Excellent. Now, because these are in series, we know that the total current that's flowing in the circuit is flowing through R3. The same IT is flowing through R2, and the same total current is flowing through R1. The same current flows through all three resistors. That is the definition of loads in series. So, from Ohm's law, what is the voltage drop across R3? Solving for E, or the voltage drop, the potential difference, we get. So the voltage dropped across R3, V3, is equal to the total current times R3. The same is true with R2. The voltage dropped across 2 is equal to the total current times R2, and the voltage dropped across R1 is equal to the total current times R1. Oh, E, yeah, I will try to make sure and remember to use V for volts or voltage. But generally speaking, when you see E as used in Ohm's law, or when you see it written as a funny script E like this, what it stands for is electromotive force. Okay? That's from the early days of first beginning to research electricity and how it worked, and people thought of the voltage as the force that pushes the current. Of course, we know that a voltage is not a force. A voltage is go back to, what page is this? Go back to page 519 and look at table 18.3. A volt is what? Yeah, but in terms of units. It's a joule per coulomb. A joule is a Newton meter. So a volt is actually a Newton meter per coulomb. If it were a force, it would just be a Newton, but it's not. So the term electromotive force is actually an inaccurate term, but it is one that was adopted years ago in the early days, and it still hangs around. And so you will often see voltage with regard to Ohm's law written as I equals E over R as opposed to V over R. I will try to remember to use V instead of E, but I got trained up on E, so. All right. No. A force is simply a mass times an acceleration. If we want to break it down to the most fundamental units, a Newton is a kilogram meter per second squared. Then a volt becomes a kilogram meter per second squared meter per coulomb. So, or a kilogram meter squared per second squared per coulomb. Okay? Don't really need to go back to all that. All I wanted to point out was that the Newton would be a unit of force, not a volt. So, going back to this. We know that whatever voltage is applied, it all has to be there. So we can set the sum of these three voltages equal to the total voltage. Which means we can rewrite it as which we can then factor out the total current. That's equal to the voltage, which is the total current, times the total resistance. And if we divide both sides by total current, we are left with the total resistance is equal to the sum of the individual resistances. When they are in series. Now, that may seem like a trivial result. You know, it's certainly what you would expect it to be if you've been trained any at all in electronics and electric circuitry. And but I want to emphasize that it is important for you to actually understand why this is true at a deliberate level and not just an intuitive, well, it's what I've always been taught and it's the way it always worked. You are, in point of fact, working on university degrees. That means when you do graduate and you go and take a job somewhere, you're not going to be the high school graduate who interned with his cousin for 3 months before he got hired on and now he knows how it all works because he's done it a lot. You're going to be the ones with the credentials, with the degree, with the education. You will need to understand this at a deeper, more fundamental level than the other guys who were just trained up by their older brothers. Okay? I really want to emphasize that to you. I want you to take that to heart. Okay? That's the whole point of being here, is that you will leave here with a deeper and a more deliberate and abiding understanding, not just the knowledge. Anyone who memorizes the total resistance is the sum of the resistances has the knowledge. What the difference between a degree and training is that you have also that understanding as to why it's true. Now let's look at the other case, the parallel resistors. Now, by definition, we know that the total voltage applied to the circuit is applied to every resistance. Right? What we don't know is the total current. We know we've got let me go ahead and draw it out. And we know that we have a total voltage applied. So the total voltage applied to R3 gives us the current through R3. Right? So we know that the total current through, not the total current, but we know that the current through I1, through volt, excuse me, got to have my coffee. Now let's see if I can get my tongue out from in front of my eye teeth so I can see what I'm saying. The voltage dropped across R1 will give us I1. The voltage dropped across dropped across R2 gives us I2. And the voltage dropped across R3 gives us I3. And if we have a number for the total voltage, we've got numbers for the resistors, we can calculate all three of the currents. Now, those three currents are not the same because even though the voltage is the same, the resistances aren't. But we do know that whatever the total current flowing into this equivalent resistance is, has to be the same current flowing out. So the sum of these three currents is equal to the sum of the three individual currents. This is conservation of charge, conservation of energy. There are any number of ways you can get there. But we know that the total charge coming in flows through. It doesn't get stored somewhere. It doesn't get dissipated. The total current coming in has to be the total current coming out. Somebody the other day talked about thinking of water as the analog to charge. This is a good example for that, where that works. Whatever comes in has to come out. So we know this has to be a true statement. The sum of the three individual currents is equal to the total current flowing in the circuit. And we know that the total current is equal to the voltage, the total voltage, divided by the net total resistance. So we have the total voltage divided by the total resistance is equal to the total voltage divided by R1 plus the total voltage divided by R2 plus the total voltage divided by R3. Does everybody see where we're going with this? Now we divide the equation through both sides by the total voltage, and we are left with 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. The reciprocal, the total resistance is the reciprocal of the sum of the reciprocals. Say again? Yeah. I haven't. Everyone understand the negative superscript means reciprocal, or 1 over? Okay. Let's look real quick at the special case of two resistors. We want to simplify this. We can multiply the this term by simply R2 over R2, which is, anything divided by itself is 1. So if we multiply this term by 1, we don't change anything. This one we can multiply by R1 over R1 by the same reasoning. We don't change anything. And that's equal to the total resistance. Well, now we can add these together. And if we take the reciprocal of both sides, you end up with that familiar formula that every electronic student learns for the special case of two parallel resistors. Frankly, if you learn how to use your reciprocal key on your calculator, you don't actually save any time or energy by doing it this way. All you do is introduce a potential confusion for the day when the day comes that you have to figure 3 parallel resistors and can't figure out what to do with the third one. What you actually could do is suppose you did not, this is a good question, this pop quiz for 0 points. What if you can't remember this formula here? What if this is all you remember, but now you have 3 resistors in parallel? How would you solve it? No, they're 3 different ones. No, you can't do that. But you could take the first 2 and turn them into an equivalent resistance. A single equivalent parallel resistance and then put R12 in parallel with R3, which would give you except down here in this denominator, you'll notice that R12 is not just R1 plus R2. So you couldn't just expand this out to like that. That would not work. But you could do this twice, or you could just remember that and do it once. And honestly, once you've learned how to use that reciprocal key, it's so easy to go 10 reciprocal plus 15 reciprocal plus 5 reciprocal plus reciprocal. What do we get for this? Has anyone done the arithmetic? What'd you get? 3.727. Yeah, repeating.
Yeah.
Yep. Wasn't that a lot faster than doing this repeatedly? Well, it was. So, now you know not just how to add resistors in series and in parallel, you know why. let's look at some examples. All right, let's start with 20 volts. R1, say 100 ohms. R2, 150 ohms. R3, 75 ohms. And R4 of 125 ohms. What is the equivalent resistance for this circuit? What's the total resistance? Who else has it? Exactly. 243.18 repeating. So that gives us a total current of? .2 or 82?
Oh, 82.
Damn, okay. What was the total resistance again? How much? 243.18? Okay. Yeah, we're gonna play fast and loose with significant digits for now. Just round to a couple of decimal places and call it good. How would it change if we moved R4 here? What was R4? Was 125 ohms? Sure it would. Now what's the net resistance? Before we had 125 in parallel with 150, and then the 175 in series with it. Now we've got 100 and 150 and 75 all in series and everything in parallel with 125. Yep. Who's got it? There you go. And that gives you a current of say again? 221 millions. Moving that resistor, just moving that one resistor over, what's that? Nearly tripled our current. How many of you have ever noticed that any time you put two or more resistors in parallel, the total resistance must always be a little less, or a lot less in some cases, but it will always be less than the smallest resistor. Let's 3 resistors, 100, 150, and 75 ohms. What, if that's what you have to work with, what is the absolute maximum resistance you can produce? Say again? No, the maximum resistance you can produce with all 3 of these would be if you put them in series and just added them together. You end up with, in this case, 250 plus 75, what's that, 325? Look at me getting brave doing arithmetic in my head. What's the least resistance you could make with these 3? Put them in parallel. I'll take your word for the arithmetic. I'm not doing a series of reciprocals in my head. But you put them in parallel, that'll give you the least amount of resistance they can produce. How many of you ever saw a car with one headlight out? What does that tell you immediately that you know must be true about the headlights, the circuit of the headlight circuit configuration? That they have to be in parallel. How many of you remember Christmas tree lights from back in the 1960s? One bulb goes out, they're all out until you find the dead bulb. That's because they used to put them all in series. Now they put them all in parallel, so that doesn't happen anymore, but it was a real problem when I was a kid. Yeah, you're to think, but eventually they did. But so, how much power is being produced in both of these circuits? Let's repeat the first one. What's the total power generated by this current, this circuit, dissipated in this circuit? How much was it? 1.64 watts. What about in this circuit? Okay. How much wattage is being dissipated in R4? Is that right? Somebody? Okay. What about here? We don't know what the current going through these are. We don't know what the voltage drop across these are. So I guess we got to figure that out. How much current is going through R4? $20 volts divided by 125 is how much? 160 milliamp. Okay, well, oh, that's not the right total current. That goes with the other one. There we are. If we've got 160 milliamp going through here, how much is going through the other three? 205 milliamps. Now, what's the power being dissipated in each of these other resistors? I squared R. Is that it? No, wait, it's power I, no, power is not I squared. Power is, the voltage is I times R, power, so yeah, I squared R gives us what? 4.2 watts. What about power here? 6.3 watts. And power through this one? 3.15. Does that make sense? All right, let's see. 3.2 watts plus 4.2 watts plus 6.3 watts plus 3.2 watts. So we're developing 16.9 watts in this circuit. So we were only delivering 4.42 watts total. Let's see here. We start with 221 milliamps and we subtract 160 milliamps from it. Does that leave 205 milliamps going through everything else? That leaves 61 milliamps going through everything else. Oh, wait, that's the one that I didn't want to read. Now, Now, oh great. Well, I hate these caps. Right. Now, what is the sum of these wattages? Now they sum to 441. So within rounding error, the total wattage, the total power dissipated in the circuit is going to be the sum of the power dissipated in every load. What does that work out to here? You've got a total current of 82 milliamps and a voltage of 20 volts. So we have a total power dissipated of 1.64 watts. Now we know that our total current through, what is this, the current through I3, through R3 and R1 is going to be the total 82 milliamps. So here we're going to lose half a watt. We're going to dissipate half a watt. And here we're going to dissipate 0.67 watts. Now, how do we find out the power dissipated in these resistors? What voltage drop across these resistors? Well, it's 20 volts minus whatever's dropped here and minus whatever's dropped there. So what's our voltage drop here at R3? I times R is voltage. So we have 0.082 times 75 is 6.15 volts. Up at the top, .2 volts. That means we're dropping 5.65 volts across R's 2 and 4. So the current through R2 is 38 milliamps. current through R4 is 45 milliamps. 45 and 38 are 83 milliamps. So again, ignoring our playing fast and loose with significant digits. And what is the power in both cases? .22 watts and 0.25 watts. So 0.25 plus 0.22 gives us 0.47, and plus 0.5 plus 0.67 gives us 1.64 watts total dissipated in the circuit. Any thoughts or questions? Comments? Is there anything about all of this that I'm overlooking? All right. Sum of this voltage is whatever's left over after you take away this voltage and that voltage. R1, the voltage drop there is simply the current times the resistance. Now, before everybody gets up and leaves, we got our lab tomorrow we're going to do on this stuff. And the way it's been done in the past, as you can see, I've been trying to get these computers up and running. They've got little programs on there that let you simulate circuitry where you can plug in resistors and ammeters and switches and turn them on and see what voltage develops and what current drops and stuff. How many of you have smartphones that you use? Okay, I was going to suggest just going to Google Play or whatever the Apple equivalent is, and seeing if you could download a simple circuit simulator. But if you've all got laptops that do this, bring them. And I will see y'all tomorrow for lab. Yeah, if you have homework. All right. Yeah, understand this. The lab that we're doing tomorrow is it's a far cry from a full SPICE simulation. So it's basically just the computer doing these same calculations really, really fast. You too.